Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry Chapter 9, and we are in 9.2, and this is 9.2 Part 2. So previously in Part 1, we discussed concentration and solubility. The concentration is the measure of the amount of solute compared to the total solution. It could be dilute or concentrated. We could express it as a mass percent, which is the mass of the solute over the mass of the solution. We could also express concentration as molarity, which is moles of solute over liters of solution. And we went over 3 different types of problems: solving for molarity, solving for moles, and solving for liters. So now let's talk about solubility. So solubility is the amount of solute that will dissolve in a particular solvent at a particular temperature. So please open up your book to page 270, and we're going to look at a table. So this table on page 270 talks about the solubility of common solids in water at 20 degrees Celsius. And as we will talk about, the solvent and the temperature are important. So here are the names of the common solids, and then solubility could be expressed in grams per 100 milliliters or percent mass. So in this one, salt, 32 grams will dissolve in 100 milliliters of solution. And then if you did the calculation, that would be 26.4% mass is as much salt as will dissolve. So you can have a 5% salt solution, a 10% salt solution, a 20% salt solution, but a 30% salt solution, not all that salt's going to go into the water. So sugar is quite a bit higher, 204 grams per 100 milliliters of solution, and you can get a 67.1. Baking soda is lower, and zinc sulfate. Marble calcium carbonate is insoluble. You can see that 0 grams will dissolve in water. Copper sulfate, Epsom salts, and glucose. So now please write this down. Solubility tables. So we talked about solubility tables, and there's the one on page 270, and then there's the one that we have been using to tell the state of matter of an ionic solution, if it would be aqueous or solid. So saturated solutions are solutions that contain the maximum amount of dissolved solute. And an unsaturated solution is a solution in which more solute could be dissolved. Looking at our solubility table, a saturated solution, salt solution, would have 32 grams in 100 milliliters of solution, and an unsaturated salt solution would have perhaps 15 grams of salt in 100 milliliters of solution. Next, we will talk about aqueous equilibrium. So this is the condition when the amount of dissolved solutes remains constant over time. It is in equilibrium. So in equilibrium, the solutes that are dissolving will balance the solutes that are undissolving or becoming solid. So let's look at page 273 in our book. So in this picture, we can see that the rate of dissolving, or the forward reaction, where these little sugar molecules are breaking off of the block of sugar, of the crystal of sugar, and going into water and being dissolved, is equal to the amount of dissolved solutes that are coming back and crystallizing into this sugar crystal. So in equilibrium, the forward reaction is the same as the reverse reaction. It doesn't mean nothing is happening. It just means that things are happening, but they're happening at the same rate. So we say 2 are dissolving, and 2 are undissolving. So in equilibrium, the solute plus the solvent is making a solution, and that is in equilibrium, or happening at the same rate that the solution is breaking up into a solute and the solvent. So the solute is undissolving at the same rate that it's dissolving. So two particles here are dissolving into the water, and then over here, two particles are going back into the solid. So let's talk about a supersaturated solution. So how can you have more than the maximum? Well, temperature is important for dissolving and for solubility. So if you heat the solution, you can dissolve more of the solute. And then when the solution cools back down, perhaps to room temperature, that solute, solution will be saturated, and the solute will crystallize out. So this is how one makes rock candy. So you get a supersaturated solution of sugar water, and you heat it up to do that, and then you put it at room temperature, and you put something in there for the sugar crystals to crystallize on, to attach to, and then you get rock candy. There are several factors that affect the solubility. So one thing that affects solubility is the type of solute and solvent. And we've been talking about this, polar versus nonpolar. So polar solutes will dissolve in polar solvents. For example, salt is ionic, so that is extremely polar, and it will dissolve in water. Whereas butter is nonpolar and it does not dissolve in water. Temperature is another factor that affects solubility, and if you increase temperature, you will increase the solubility. So if you want more sugar to dissolve, you will heat it up. So more sugar will dissolve in hot tea or hot coffee than will dissolve in cold tea or iced coffee. So factors that affect solubility when we have a gas in a liquid, and that's often different than having a solid going into a liquid. So pressure is really important when we are looking at the solubility of a gas in a liquid solvent. Not so important with solid solutes going into liquid, but gas, very important. So if you increase the pressure, you're going to increase the solubility. So if you think about a can of pop, that is carbon dioxide gas dissolved in a liquid solvent, which is basically sugar water. And so if you have it at normal pressure, then the gas, a lot of the CO2 goes out and your pop goes flat. So you have to increase the pressure and keep it in that can or bottle or whatever it is to increase the solubility to have more carbon dioxide in the liquid. Another factor that affects the solubility of gas in liquid solvents is temperature, but it's the opposite. So if you increase the temperature, that's going to decrease the solubility of gas. So for example, if you have a hot bottle of pop, it has less ability to dissolve that carbon dioxide than if you had a cold bottle of pop. So if you have a warm bottle of pop, you open it up, all that carbon dioxide is probably going to come fizzing out because it does not want to be in the liquid. It is not as soluble in hot temperatures. So those are the factors that affect solubility, how much of the solute will fit in the solvent. Now let's talk about factors that affect the dissolving rate of aqueous solutions. And to be clear, this does not change the solubility, only how fast the solute dissolves. So how fast a solute will dissolve, not the total amount of solutes that do dissolve. So increasing the surface area is one way to make a solute dissolve faster. Stirring is another way to make the solutes dissolve faster. Heating is a third way to make solutes dissolve faster. So let's look at some pictures. So as we talked about increasing the dissolving rate, so getting things to dissolve faster, One way to do it is to increase the surface area by breaking it up into smaller particles. So if you make them into a powder, they will dissolve faster than if you just have a chunk of the solute. So you can see when there are little particles, there's all these spaces where the water can get around and start to dissolve, as opposed to only having a couple of places where the water can get around and dissolve. Another way to increase is to stir it, which means you will have more particles reaching more molecules of water, and it's more likely, and it will dissolve more faster. And then a third way is to heat it up. And if we look at this picture here, dissolving in a collision process in slow, cold molecules is not as effective as hot molecules. So the water is actually moving faster, so you'll have more bumps against this salt crystal if it is hot, and then it'll dissolve faster. So how do we prepare solutions, whether looking at saturated or unsaturated, or the rate at which we're dissolving, or the solubility, if we're going to increase the solubility? So with all those factors, let's just think about the solution itself. So please turn to page 277. Many lab experiments require a solution of specific molarity, and being able to prepare a known molar solution is an important lab skill. And also, if we know the molarity of the solution, we know how many molecules and how many moles of a certain solute are in there. So the first thing we would do is we would determine the grams of the solute needed by multiplying the moles by its formula mass to get it in grams or mass. And then we would mass that out on a balance. And then we would add the solute to something that looks like this, which is called a volumetric flask, which we do have at Lafarge. And then you would fill the flask about 2/3 of the way up with distilled water. And then you would swirl it or have it use a magnetic stir bar until all of the solute was dissolved. And then these are supposed to be very precise, and there's a little line there, and we would put water all the way up to that line. And that is the most precise way of getting an exact amount, as opposed to putting like 10 grams and then 100 milliliters of water. We want to make it so that it's 100 milliliters of solution. So we put the solute in, and then we add enough water, let's say to get up to 100 milliliters. So we have exactly 100 milliliters of solution. However, solutions are often made by diluting concentrated stock solutions of known molarity. So let's talk about how to do that. So adding water to solution does not change the number of moles of solute, it only changes the concentration. Let's say I have 100 grams of salt in a solution, and I add another 100 milliliters of water to it. I still only have 100 grams of salt, but now it is less concentrated. So we are going to use the equation, and then you would just solve for the unknown. So please write this all down. Molarity of solution 1 times the volume of solution 1 is equal to the molarity of solution 2 times the volume of solution 2. In other words, M1V1 equals M2V2. In the next part, we're going to go through one of these calculations together. So we're going to figure out, for the lab, we need 150 milliliters of 1.0 molar HCl, and the stock solution in the acid cabinet is 12 molar. What do we do? So, to be continued.